Our next speaker is Leanna Leverich. She is a PhD student working under Dan Kaiser, working on her doctorate degree. And her research focuses on spatial variability and agricultural management. And her presentation will be entitled Potassium Testing Based on Mineralogy. Let's welcome Leanna. As long as we're waiting here, just a reminder to please fill out those surveys throughout the course of the day. And there is a scanning code on each table. You can scan that with your phone to get to that survey. Are we all set?
I think you can just hit the arrow. It's fine. All right. Hi, everyone. Thank you for bearing with me while we just iron out a little bit of technical difficulty. So like I was said earlier, I study potassium with Dan Kaiser. I've been working with him in soil fertility for quite a while now. I used to study phosphorus before I moved into the potassium realm. And as was prefaced before, Dave brought up that there's some issues with clay type and potassium response. And so that's what we're really trying to dig in here at Minnesota, is to look at, okay, well, what are our different mineral types? How are these clay types really affecting our potassium responses? So just to dive into just basic mineralogy here before we get too deep into the data, we have to consider our major potassium pools in the soil. This is review for a lot of people, but it really sets up the basics of mineralogy and how that's going to affect potassium. So obviously you have your soil solution K here, and that is the potassium that is readily available for plant uptake. So this is already in the soil water. It moves by diffusion up the plant roots, and this is ready for uptake. But when we talk about mineralogy, we have to focus on our mineral fractions here that we have in the soil, which is our mineral K, our fixed potassium, and then our exchangeable potassium. So when I say mineral potassium, you can kind of think of this as the actual minerals that are in the soil that are very tightly bound. This is not readily available to the plant. This weathers very slowly over time. And as chemical processes happen over decades and hundreds of years, that those mineral pieces become broken down and then release potassium. These minerals, I'm going to talk about many of them. They don't exist alone as one single mineral type. Many of them are mixed. So in the soil, you have many types of minerals just kind of conglomerated all together. And we're trying to look at all those types and how the different amounts of those relative types of minerals are impacting potassium. So you have your mineral fraction, which is not available, not readily available. And then you have your fixed potassium. So this is potassium that is within clay layers, but what happens is it slowly weathers. It will weather a little bit more quickly than the mineral potassium. And so like things like really dry conditions will cause the layers of that clay mineral right there to curl, and it could release that potassium. So when we talk about soil testing and you have your dry versus your moist potassium, some of the differences between those moist and dry analysis are due to this fixed potassium, which is caught in those clay interlayers. Then our last fraction is our exchangeable potassium. And this is what's measured when you do your CEC measurements, when you measure with a potassium soil test, along with your soil solution K. So this is the potassium that's sorbed on the outside layers of the clay. It's sorbed to the sites for the CEC and also to your organic matter. So this K is ready to be interchanged, adsorbed, and desorbed with the soil solution. So that's readily available. So clay minerals, like prefaced before, they're very unique in their interactions with potassium. You have sand and you have silt, and those are both, they're kind of like round, or you can think of them as like marbles or gravel in a glass, the way that they sit. And the way that they sit really impacts how the mineral can move, or how fertilizer ions can move around. Whereas clay, it sits like plates. So you can see this big difference between how silts stack and sand stack versus how clays stack. And clays are layered and they are charged. They have ionic charges in them. And these charges and the way that this clay is layered, that impacts how a potassium ion can sit inside of that clay. So these are pictures of clay minerals under the electron microscope. Illite, smectite, and kaolinite, those are types of minerals. And I'm going to go into a little bit of detail about them because we're going to be looking at K recommendations based upon these minerals. So the first type of mineral that I want to cover is kaolinite. And kaolinite doesn't have much interlayer space. It's a 1-to-1 mineral. So you can think of kind of like sand properties or something, kind of clays that you would find in sandier soils. They have a low CEC and they don't bind anything in their interlayer space. And when I say interlayer space, I mean this space right here. So there's nothing to bind there. They stack on top of each other. The next mineral type is illite or mica. Illites and micas are 2-to-1 minerals, meaning that they do have an interlayer space, and they are unique in that they fix potassium. So when I was talking about potassium that can become fixed in the interlayers, this is what I'm talking about here, is these types of minerals cause that. They trap potassium in their interlayers, and they have a moderate CEC. The CEC allows for potassium, magnesium, calcium to bond or bind on the outsides of these minerals. And then we have smectites, and these, Dave mentioned these in his talk, these are the shrink swell clays. So these can really expand very widely in their interlayer space when there's a lot of water, and we call that hydrated. And when it's really hydrated, a lot of ions can flow in and out of that interlayer space. And it can hold on to K or release potassium in that interlayer space as well. And this kind of contributes to having a higher CEC on the edges of the clay, as well as kind of allowing for cations to go in and out of that interlayer space. I will mention though, when it's very dry, you have the shrink part of this shrink swell clay, and it can actually collapse that interlayer and trap potassium and other ions, which can also have an influence on our soil tests. So what we're focusing on specifically in Minnesota when we're looking at K recommendations is really these two types of minerals. There are dozens of types of minerals out there, but we're really going to focus on illite and smectite for these very specific properties that they have and the way that they interact with potassium. So this is not unknown. This is actually kind of built off of work that's already happening in North Dakota, where they've begun to map some of their clays and modify their potassium recommendations based upon the different amounts of minerals that they have there. So these are maps that were created a couple years ago, or just a year ago or two, from Dave Franzen, and I'm not sure if Brecker worked on this, but anyway, this covers K feldspar content, smectite to illite ratios, and ratios of smectite to other clays, etc. And they kind of identified this very specific breakpoint in their smectite to illite, and it was a 3.5 ratio, which is this map down here. And we're also going to talk about the 3.5 ratio for soils of Minnesota. Something to point out is that clay spatial variability is not at all like your routine soil test. Clays and clay minerals and abundance is going to vary more on like a square mile basis or on a county level basis. Here I have a picture of the geology on a county level for Minnesota. So this is kind of more like what we would expect a clay map to look like. It's going to be much lower resolution. Whereas, if you do a soil test for potassium across your farm, you're going to have variability across your whole field. We don't anticipate having different clay mineral abundances or ratios across fields, nor really across farms, unless your farm just happens to be kind of on the border of two different geology types of some sort. So clay abundance is very much determined by the soil forming factors such as climate and previous geology of the site. So that's what you can expect to see. You're going to have kind of one major clay mineralogy group for your whole entire farm. So what we did is we took a bunch of samples from Minnesota, and we are looking at the actual mineral makeup. We have sampled many of these sites, and I'm giving you a photo of what we've sampled so far and what we also have but haven't processed into this data set. So this is with a grain of salt. We have yet to add about half of our data points to our data set that I'm presenting today. So expect to see changes in the future here as more data comes in. One other thing to point out too is that the soil samples are very much in our highly agricultural area in the south. That's where we have most of the samples as of right now. So we're going to have a finer resolution or a better resolution or a better mapping so far in the southeast or southwest corner than we do elsewhere, but we will add more samples to the map. At many of these locations, we conducted on-farm trials. This is an example of one of the trials that took place. What we did is we just built these right into the prescriptions for growers. So this was spread with their spreader. Usually we did aim to have 2 passes with the spreader, so usually around 140 feet, and applying 5 different rates, anywhere from 0 pounds of potassium all the way up to 160 pounds of potassium. We aimed to put these trials on farm fields that had low to medium testing soils so that we could get a response. As many of you know, sometimes that's not always the case and you don't get a response, which you'll see some evidence of in a bit. So each of those locations too was tested using an XRD analysis. This is X-ray diffraction is what XRD stands for, and it outputs this graph. And this is kind of a relative abundance of all these different minerals. What's important to mention here is that these are semi-quantitative amounts. We don't have the precision that we do with pH or with potassium or with phosphorus, where we can really nail down that one specific number. With clay minerals, we are looking at relative amounts of each type of clay. So we get a relative number for smectite and illite and kaolinite and so on. So we have to, that's why ratios have been kind of beneficial to us, is that they put in more relativity. So what we want to do with this research project is really to map out our different clay minerals for growers to reference should we get recommendations updated for specific types of clays. We want to look at the clay species specifically and see if we can optimize our K critical levels, and then also determine if our fertilizer response is different based on the clay mineral abundance. So first, looking at what we have mapped. What does our Minnesota mineralogy look like? Once again, I want to remind you that this map is going to be better for the southern half thus far. We will improve the map, and it will use other covariates across the whole state so that we can map better northern areas where we don't have as many samples. But just looking at feldspars, something to point out right away with feldspars is that the scale is from 3.6 to 5.6. So there's not a whole lot of spread or difference right now in the data that we see or that we have for K feldspars. And most of that variability is happening down here where we have lower feldspars in the southern part of the state. And then as you move up towards the river here, it starts to go up a bit. Kaolinite. Kaolinite is our low CEC clay, if you remember. You would see this behavior, or kaolinite would have a behavior kind of more like sandy or silty soils, not such a heavy clay soil. You can think of kaolinites often are with quartzes, and they're not that sticky, heavy clay. So of course, our lower amounts of kaolinite are along this Minnesota River basin line. And then as you would expect, kind of in our driftless region and in our central sands area, you see more kaolinite, which is what you would expect to see. Now, if we look at smectite and illite, they have inverse relationships with one another. Where you have more smectite, you have less illite. And where we have the heavy amounts of smectite is again right in this middle area of the state, just kind of around Renville County, right along that river area, river basin, also towards Lamberton. So that's where we're having the high smectites. See, again, that's kind of what you would expect, kind of heavy, sticky clays. Illite, of course, is inverse of that. We see that illite is more so in the eastern part of the state, northern central area, where you'd have the sands. And the illites, again, they behave like kind of like kaolinite does, where they act more like a moderate CEC type of clay and soil. So, oh, that's a bummer, that didn't pop up. All right, well, I'll kind of describe this. So this is just to kind of give a light overview of illite and smectite, just to reiterate that there is an inverse relationship between illite and smectite. The higher you have illite, the more illite mineral that you have in your soil, the less smectite that you have, and it goes vice versa. And this relationship was also found in kaolinite. So kaolinite, it has higher amounts of kaolinite would mean less amount of smectite in your soil. So they tend to just be inverses of one another. So like I said, in North Dakota, they used a smectite to illite ratio, and this is simply just smectite divided by the illite relative abundance. And a higher ratio would be more smectite, and a lower ratio is more illite. So think stickier clays, heavier clays, and the smectite, the illites are more of the sandy characteristic soils. And as we look at that ratio, just like you saw with the smectite to illite maps, you would expect to see a higher ratio kind of where you had the high smectites, which was right in this area here. However, we see that the ratio starts to come down a little bit in this bottom corner, a lower ratio up through similar areas to the illites, the prominent illites, where it's in the eastern part of the state and the central part of the state. I know I haven't talked a lot about the northern part of the state, and that's because we don't have a whole lot of data points, and so I don't want to give the wrong idea. There was pretty heavy smectite up there as far as numbers. I just don't think that we're able to interpolate that quite well enough yet. So how does this clay ratio really impact our soil test K, and how do these clay species impact our critical soil test level? So just to kind of reiterate what I'm talking about with soil test K, I'm going to talk about fertilizer, and then I'm going to talk about soil test K. So soil test K is the point at which we don't see an increase in yield with a higher soil test level. So here's our relative yield on the y-axis and on our x-axis, we have our soil test level. And at 95%, that's where we consider, if we fit a curve here at 95%, that's the point that we consider it to be the critical point, the point at which we don't have a yield response. So looking at just our curves before we have any fitting, I just want to point out that you can see an abundance of illite throughout this entire curve. Illite is the dark points here. And if we look at smectite, you can see an abundance of smectite across this whole curve. So you are not constrained by your yield success is not constrained by the type of clay that you have. You can still achieve just as high a yields in any type of soil. It's just that we want to tailor our recommendations based upon that. So what we did is we used the 3.5 ratio point that North Dakota had used in the past to break apart our database of our K response rates by high smectites and high illite soils. So high illite soils would be under the 3.5 ratio, and high smectite soils would be above the 3.5 ratio. We did a number of cluster analyses to look at what were the factors that really influenced where this data set split. And after looking at multiple different methods of clustering, really the 3.5 ratio worked just as well as some of the more advanced clustering methods. So it's a good marker right now. So what we can learn though is if we look at our critical soil test level. For our illite soils, the critical soil test level was 85 parts per million. And in the high smectite soils, the critical soil test level was 106 parts per million. So this would be kind of the point where we flip, from this is where we would start considering this like a high testing soil. So our low and medium might be on one side and the high and very highs are on the other side. So maybe what this tells us is that we can change our soil test classifications based on smectites and illite soils. So you might be able to shoot for slightly lower soil tests in illites versus maintaining your soil test at higher rates for smectites. This just reiterates what we did is we plotted a critical K level for every site that we had. And if we look at this relationship, we can see that the smectite to illite ratio slightly increases as you increase your critical soil test value. So as the amount of smectite in the soil increases, your critical soil test K level will increase. And that means that as smectite increases, the soil test K level might need to increase to achieve maximum yield. And we can infer from this that possibly in higher smectites, that might mean that you need to apply more potassium fertilizer in order to meet your optimal yield. But that's another question yet. So looking at our field trials, I'm going to go over a few field trials, not all of them. But so this might look familiar to you. This is just a simple rate response. We have our K rate on the x-axis, and then on the y-axis, our grain yield. And these are two great response curves from one is a plot trial, one is an on-farm trial. Looks great. The optimal K rate on this trial was 65 pounds per acre, and the soil test level was 118 parts per million. And here on this other soil, the optimal K rate was 107 pounds per acre, and the soil test level was 81 parts per million. This may be due to the fact that maybe some of the soil was supplying some of that potassium at the one site versus the other, or possibly other mineralogy issues. However, we saw some trials that look like this, which I think a lot of people are familiar with seeing, all of a sudden you don't get a response from potassium. And why is it that we're not getting a response? So just to preface this next chart that I'm going to show, any responsive site is going to be signified by a triangle. Any site that was not responsive, I'm signifying by a circle. So here we have our non-responsive sites right here, all these circles. And then we have our triangle sites, which were responsive. So you can determine an optimal rate for them using an algorithm, but that doesn't necessarily mean that applying anything would have been beneficial. So what we can see here is there's a very clear line, like at 150 parts per million potassium where we didn't really see a response at any of those farms. And then intuitively, you would think that as you increase your soil test level here on this x-axis, your optimal rate would start to come down. But we don't see just a nice clean curve where it's just follows this curve all the way down from, around 80 down to 150. So what is causing that? So we looked at different minerals and saw if they have any significant relationship at all with optimal K rate. And illite did have a significant relationship when we did run the statistics on this. And it showed that soils with lower illite abundances required higher potassium applications. So that kind of plays right into the smectite question as well. So we have higher smectites usually means lower illites. Lower illites need more potassium. Higher smectites also seem to want to maintain at a higher potassium level. So there is a little bit of some correlation going on here between the illites and the smectites and how they're responding with potassium in the soil. So that's kind of what I have to present to you today. We are still working on this. Like I said, we're going to have updates coming out soon, hopefully with mineralogy considered and sands considered. But critical soil test tends to be higher in higher smectite soils, and low, medium, high, and very high classifications. Something that we could do in the future is vary those across the different mineral types or across clay ratios. And then as far as fertilizing and response, we do see a significant relationship with illite and the amount of illite in your soil and also your K response. And as we dig into this more, we'll be able to reveal if that lower illite indeed does require more potassium fertilizer. So not any changes yet to the recommendations that we have, but you can expect to see those updates sometime in the future. We are creating maps for the dominant clay species across Minnesota for growers to reference, and I have all of the maps updated to ArcGIS online if you want to follow our progress and just watch as these maps improve. And also as well, you can expect to see some sandy soil K recommendations that kind of go along with this mineralogy piece as well. So that's kind of what I have, and I'd like to thank you all for your attention, and I'm happy to take any questions that anyone might have about mineralogy or how this might be impacting potassium. Thank you. All right. First question, when soil tests are conducted, is the illite and smectites levels requested? Is this a special test that would need to be done above and beyond typical soil tests? Yes. So yes to the second part of your question. Testing for illites and smectites or any type of mineral in your soil is very, very expensive. It is not something that we would recommend that you go out and do it on your own. It'd be very expensive. They run around like $350 a pop per sample. So you don't really want to be testing your farm for your smectites and illites. So that's why we are creating a map for farmers to reference themselves. So it'll be like a lookup map. You can see what zone you're in for what ratio or what smectite or illite content. And then you'll be able to reference that for your future K applications. And when the soil tests are conducted, yeah, so we don't have illite and smectite levels at this point characterized for the state. That hasn't been done yet. So that's just part of the aim of this work is to characterize the state. All right. Are we going to have K guidelines based on clays in Minnesota, and when would that happen? The answer is hopefully. If this study does yield, good responses that are reliable and something that we can actually feel confident about modifying, yes, we would like to have, especially looking at smectite and illite amounts in the soils, guidelines that are segregated out between smectites or illites or based upon that ratio. Kind of in the same vein, sands do behave quite a bit differently, and so that for sure is going to be updated. That does kind of play along with the mineralogy, as sands tend to have, higher micas, illites, whatever. When that's going to happen, Dan, do you have any advice? Sometime this year. So, and what is the benefit to using a moist K test? So, it's going to give you a different characterization of your soil potassium for sure, but the reason why that we use the dry test is it's because we calibrate and we use calibration and correlation to create a database so that we are able to give recommendations based upon a specific test. So we use the dry test for all of our recommendations from the University of Minnesota. Using a moist test is maybe just not going to quite fit into our typical recommendations that we use. There's nothing necessarily wrong with using the moist test, it's just not going to fit our set of recommendations. Yep. Sure. And what I can do is I'll also, if you can jot down this web address here, that also gives you access to all the maps too. And which map were you interested in seeing? The ratio or the illite and smectite? Oh, sure. Yep. So that was just a simple IDW interpolation that was made. Sorry? Oh, yeah. So his question was about what was the interpolation method that was used for the points. It was an IDW that was performed for this, but this is more than to be used as a map to locate exactly what your soil test was. This is to show relative differences across the state. To actually interpolate this map, we're going to use a random forest model to use covariates and other raster layers to actually make a real map. Yep. Mm-hmm. Yeah, so that could be when I was talking about clay fixation, when you have really dry, sorry? I'm sorry, yes. Yes, so there was a question about uh, when you are sampling in super dry conditions versus in moist conditions, why is it that your soil test is so different? And also, why is it that your soil test K might be higher than what it actually is in reality in moist conditions? And so part of that fixation question is, as the soil really dries out, sometimes those layers begin to curl and it begins to release more potassium. So that could be part of the mineralogy piece as to why it is that there are higher numbers. Typically, we just recommend trying to sample under the same conditions year to year so that you are able to compare that. It's tricky. Yeah, I'm sorry, I don't have a better answer. Okay, and another question, can smectite and illite content be correlated to, for example, soil parent material to extrapolate from your point measurements rather than inverse distance? Yes, so the maps that I showed today are a very simple interpolation method where we just are looking at the points around each other and it creates a raster or a map based upon the actual point values. When we're actually creating an actual map for people to reference for themselves, we're going to use a much more advanced method using a lot of things like soil parent material, the underlying geology, many of the geological principles, climate, anything that would be considered a soil forming factor, to actually use those covariates to help guide us in making that map. So it'll be a much more robust map and it'll be very much validated and cross-validated so that we have a more accurate representation, given that we don't have samples to cover the entirety of the state. I hope that answers your question. Anything else? All right, well, thank you so much.